Welcome back to the Thermodynamics exam walkthroughs. We're going to be going through questions on thermodynamics. Today we'll be looking at 2024 October Unit 5, question 11 and question 12. So if you want to try the question, which you should, pause the video, do the questions yourself, and then come back and see the answers. How I solve it, and if you just want to see the mark scheme and the examiner report, you can go to the end of the video. So in the first question it says, helium gas can be used to fill balloons. A cylinder of helium gas contains 1.2 times 10 to the power of 24 molecules. The temperature of the gas is 293 Kelvin. Calculate the internal energy of the helium gas. We should know that internal energy is equals to kinetic energy plus potential energy. And in an ideal gas, the potential energy is equals to 0. So the internal energy is just going to be the kinetic energy. And we can calculate the kinetic energy for one molecule using the formula Ke. The mean Ke is equals to 3 by 2 Kt. And you should get the mean kinetic energy for one molecule of helium gas as this much joules. Now we have 1.2 times 10 to the power of 24 molecules. So I'm just going to multiply this by 1.20 times 10 to the power of 24 molecules to get the total internal energy of the helium gas, like all of the helium molecules combined. And we should get an answer of 7,278 joules. And if we round that to 2SF, we should get 7,300 joules. Okay. So that was the answer to that question. Let's move on to this question. Question number 12. Bronze is a mixture of tin and copper. Tin melts at a much lower temperature than copper. 2.7 kg of solid tin is at a temperature of 295 Kelvin. Is added to 10.5 kg of molten copper at a temperature of 1520 Kelvin. The tin melts and mixes with the molten copper to form molten bronze. Calculate the final temperature of the molten bronze. And they've given you the specific heat capacity of molten copper, specific heat capacity of solid and molten tin, and they've given you the specific latent heat of fusion of tin. So we have copper at a temperature of this much, and then we have the mass given, and what's going to be happening is energy is going to be going from copper to the tin. The reason is that copper has a higher temperature and it also has a higher melting temperature as well, which we can see right over here. So copper has a higher melting temperature and also a higher temperature over here of 1520 Kelvin. So the energy will go from copper to tin. And tin will take that energy and it will melt, and then the rest of the energy that will be there, that will be used to change the temperature of tin. And we have to find that final temperature. So it's going to melt first, and then it's going to go from 295 Kelvin to some temperature after absorbing the energy from the copper. And we have to find that temperature. So let's form an equation and then we're going to solve it. So this is going to be the equation. Energy from copper to go from 1520 Kelvin to a lower temperature. The reason copper is going into a lower temperature is because it's transferring energy to the tin. And then that is going to be equals to the energy to melt the tin plus the energy absorbed by the molten tin to go from 295 Kelvin to a higher temperature. Again, the reason for the higher temperature is because the molten tin is absorbing energy from the copper. So copper's temperature is going to go down and the temperature of molten tin will increase. So here I have put everything and I've put it in the formulas. So here we have this formula MC, change in temperature. So we have the mass of copper times the specific heat capacity of molten copper times the change in temperature, and then we have the mass of tin times the specific heat capacity of solid and molten tin times the change in temperature plus the mass of tin times the specific latent heat of fusion of tin. Now, one thing that you have to be very careful with here, which most students miss, is that you must make sure that this change in temperature and this change in temperature, they both are different, obviously, but they also must both be positive. Once they are positive, then only will this equation work. Otherwise, it won't work. And the reason why both of these have to be positive is because of energy conservation. Now, let's take an example. Let's say we had A. A had 0 joule of energy and B had 5 joules of energy. B transferred energy to A. Now, A has 5 joule energy and B has 0 joule energy. So the total energy is going to equal to 5 joules. Energy transferred to A will equals to energy transferred from B. And that will be 5 joules is equals to 5 joules. 5 joules of energy was transferred from B to A and A got the 5 joules of energy. Now, can we put negative signs here? Now, A got 5 joules of energy. And the energy transferred from B, let's say, since energy was lost, we put minus 5 joules. Many students, they think like that. Okay, energy is being lost. Let's put the minus sign. It makes sense. But that's not correct. Because the reason is, if you do 5 joule, you move this to the other side, plus 5 joule, we are going to end up with 10 joules. This is totally wrong because the total energy, remember, was 5 joule. But here it's showing us that the total energy is 10 joules. We have just created energy out of nowhere. So this is going to break the energy conservation law. So we cannot do this. Now notice in the example above why it makes sense. Notice if I move the 5 joule to the other side, it's going to be 5 joule minus 5 joule. We can see that the total energy is going to remain the same. There is no change in energy, no new energy is created. This 0 here shows us that it was 5 joules initially. Now it's also 5 joules. But in the example below, we are breaking the energy conservation law. So that's why we have to make sure our both sides are positive. So now I've plugged in everything, but I haven't plugged in the temperatures yet. So we can see here that we go from 520 Kelvin to a smaller value. So what I'm going to do here is I'm going to do 520 minus the final temperature. If I do it the other way around, we can see that final temperature minus 520. This will give me a negative number. I do not want that. Now for tin, we can see that it goes from a smaller temperature to a much higher temperature. So we can just do final minus 295. If you do the other way around, you're going to get negative. We do not want negative numbers here. Okay, and now what you're going to do is you're going to solve this. So once you solve it, you should get an answer of 1386 Kelvin. So you're going to solve it algebraically and then you're going to get the answer. So hope these two questions were clear. I'm going to show you the mark scheme and the examiner report and then we'll end the video.